Hello again. In this video, we're going to show how to do some fractional crystallization calculations that we'll use to try to model the monocrator system. In an earlier video, we explained how to set up this part here, the individual KD values that are used in conjunction with these mineral proportions to produce these bulk distribution coefficients here. So we have these D values. They will be part of an equation. I have two sheets open, by the way. We have this modeling magmatic processes sheet where we have this equation. That D value that I just showed you in Excel is this D value here. So let's explain this equation. This equation is for perfect fractional crystallization. It gives us the composition of a liquid if we have an original liquid that has crystallized some certain amount. How much? Well, that's determined by this value F right there. That value for F is the melt fraction. So if F is, let's say, 0.7, that means that we have 70% liquid left over from the original liquid that we started with, which is the same as saying that the system is crystallized by 30%. So the concentration of some element in the liquid is going to be equal to the original concentration multiplied by the amount of melt that's remaining, expressed as a fraction, when that fraction is raised to the exponent of d minus 1. So let's go ahead and enter that equation. So first we'll deal with this quantity F. So down here we have melt fraction. We're going to let melt fraction go from a value of 1, so we have 100% liquid, down to 0. And we'll do it in increments of 10% crystallization. And to go from 100% liquid down to 0, I'll just grab both of those cells, move the cursor till it turns into a black cross, and then do a fill down command. I'm just going to do a fill down command until I get to 0. As you'll see, this will actually blow up when we enter the equation, but we'll look at that a little bit later. We're going to change that to be 1% or 5%. So there are our values of F. We just make them up. We let it be whatever we want. The smaller the increment we have, then the smoother the curve and the more finely tuned our model is. Now for our model, we also need an original composition. So if we go back to this equation, what is our starting liquid? Well, let's go back to the sheet. If we take magnesium versus calcium, in an earlier video, we showed that these fellows here are the primitive lavas. Those are our starting liquids. That's the stuff that first enters the magma chamber, then sits there. It will sit there and cool and crystallize. And as it crystallizes, the residual liquids apparently move in this direction, or at least that's the thought when we establish this model. And so we can choose any one of these guys up here as a possible starting composition. Let's take this guy here that has 4.32 weight percent MgO. So for our data sheet over here, we'll look for the fellow that has 4.32, and we can simply take that data and copy it over. But before we do so, we need to make sure that all of our labels, all of our columns line up. I'm going to put that in red font just to remind us that that's where we want to go for our initial composition. But take a look at the modeling sheet here. I have silica, titanium, aluminum, iron, no manganese. We skip over manganese, go straight to magnesium, and we're not modeling chromium or phosphorus as well. And so since we have those misalignments, I'm just going to pull out this. I'm just going to delete manganese. These are at the end. I'm just going to delete those two, although I don't really need to. And that way, the oxides here are now in the same order as the oxides here. And that allows me to grab this data here in red and hit copy, move it over to the modeling sheet for my parent magma composition, and just hit paste, and now all those oxides will match up. If we wanted to, we could insert a column for manganese and then insert some KD values for that and for chromium and phosphorus as well. But here we're just going to simplify matters by pulling them out. So now we have a possible starting liquid composition. Is it the best choice? We don't know. We could play with that later. But for the time being, we just want to see what the effects are if this is the starting liquid, C0, and this is the value of D. Let's go back to this. We're going to enter this equation here. We're going to calculate this. which is equal to that stuff. So it's this part here that we are interested in now. The product of C naught multiplied by F to the D minus 1. So let's go back to the sheet. We're going to calculate liquid compositions for all of these oxides, where the composition of the liquid is equal to C naught, that's this guy here, multiplied by F, that's this fellow here, raised to the power of D minus 1. Now, when we fill down and fill right, as we fill down, what we want to do is hold this row and this row constant. So the 18 and the 22, we want to put dollar signs in front of those, because as we fill down, we don't want to shift the reference to these D values or the C naught composition. So notice that as we fill down, we're still capturing row 18 and row 21 for our D and C naught values, but we didn't put a dollar sign in front of the row for C, because we do want to capture those variations in the values for F. Notice that when F is 0, the system is 100% crystallized, but now the calculation, the formula blows up. Well, Excel is not going to want to plot this division by 0 problem, so we'll just put in 1%. Well, that still gives us a very, very unrealistically high silica content. Let's change it to 5% liquid left, 95% crystallization, and we'll use that as a placeholder for the time being. Now, if we fill right, we still want to refer to column C, so I'm going to put a dollar sign in front of column C. Then we will fill right and fill down for the rest of these. So now we have the calculated liquid compositions here. These are the Cl for silica, titanium, aluminum oxide, etc. And if I just grab an arbitrary cell over here, notice that I'm correctly capturing the D value, the initial, the parent magma composition C naught, and then the corresponding value for the melt fraction F, 60% liquid or 40% crystals. So it looks like we're doing okay here. It's good to just click on a couple of cells to make sure that our calcium refers to the calcium input values, the calcium output refers to calcium input, and so it looks like we're doing okay with these cells. What we will do in another video is take these values here and plot them on top of our data to check whether our model of perfect fractional crystallization, does a good job of predicting what we see in the natural data. Keep in mind that all of these values are linked to these mineral proportions. So for example, we have an MgO content over here at 50% crystallization. That's just a little under 1% MgO. MgO is a compatible element, and so as we crystallize olivine, we are pulling out some of the MgO out of that system and causing the MgO to decrease. What if we increase the plagioclase content to 70% and made the olivine, let's say, 30%? The D for MgO is much smaller, it's still compatible, but now we have a lot more MgO in the residual liquid because we're not pulling it out as fast. We have less olivine in the system, so there's less MgO going into the crystalline phases. So all of these numbers here are closely tied to these mineral proportions here. They also depend on what we used for a starting composition. If we go back to the monocraters data, instead of picking something with an initial composition of 4.32, we could have taken this guy here with a composition of, let's say, 4.16. It has a little bit lower of an MgO content, but it's not completely unreasonable as a parent liquid composition. And if we insert that set of values here, you'll notice that all those values are updated. So keep in mind that these model values are sensitive to the starting composition, the mineral proportions, and they're also sensitive to the individual distribution coefficients that we put up here. So it's a model that's very flexible. In your tests, you're going to want to plot these oxides on top of the natural data, again, as we'll show that in another video, but you're also going to want to change things like mineral proportions and parent magma compositions to do your best to try to explain the natural compositions.